All right, students, welcome to our last lecture for this week. It's going to be about integrated rate law. So integrated rate law is basically a way of determining what is going to be left over or what's going to be made in a reaction after a certain period of time. So you've actually already had some exposure in your nuclear chemistry chapter to first order integrated rate law. That is what described the rate of decay for nuclear decay processes. That was a first order. We're going to have other orders as well. Zero order and second order is what we're going to focus on. So let's state the integrated rate laws first. So the key thing about an integrated rate law, what makes it different from the standard rate law, is that it includes time as a variable. So we can figure out how much time has passed or how much time must pass until the reaction proceeds to a certain point. So the first order rate equation, or rate law, was given in this way. The rate, which is specifically written as delta A, concentration A over delta time, negative if it's a reactant, and we write the rate law for reactants, is going to be the rate constant times the concentration of our reactant. Now, I'm going to show you, basically, I'm going to show you a little bit of calculus in case any of you have calculus, to show you kind of where this comes from. You don't need to understand what's going on here, but I just want to show you why it looks the way it does if you have some exposure to calculus, and also kind of just show you that this can be, once you get experience in math, you don't have to memorize these. I don't have these memorized, for example. So if we're writing the rate here in calculus terms, we would write this as d concentration A dt, and it's negative because its concentration is decreasing. And so that's going to equal K times the concentration of A. Now, if we multiply both sides by dt and divide both sides by the concentration of A, we'll get this. Concentration of A will cancel, and on this side, multiply by dt, divide by concentration of A. This side dt cancels. And so we get on this side negative 1 over the concentration of A, d concentration A, equals K dt. All right, now what we're going to do is do a process which is called integration. And integration is essentially, as you guys saw earlier, there was concentrations of A versus time. If we want to know how much is left at a certain period of time and how much has been used up, we need to add up everything that's happened beforehand. And that's what integration does. It's a fancy calculus way of adding up everything that happened before a certain time t. And so we're going to do that. We're going to integrate from time 0 to time t, and so we get 1 over concentration of A d concentration A equals integral from t to 0 K dt. Now what I'm going to do is I'm also going to multiply both sides by -1, so I can put the negative on the other side. So this will give me 1 over concentration of A d concentration A equals, and I'm going to take the K out as well since it's a constant, negative K. So if any of you know calculus, you might know what I'm doing. If you don't, it's okay. I'm just going to show you that with this funny looking math, we can actually get what it is that you'll see coming up. Okay, and now we're going to do the antiderivative, or the integral, and when you do the antiderivative of 1 over something, you get the natural log of that thing, and we're going to evaluate that from time t to time 0. And over here we're also when we take the derivative of 1, or sorry, the integral of 1 over the time t, we're going to get negative k, and our integral will be t from time t to time 0. And ultimately we get the, here we're going to get the natural log of a at time t minus the natural log of a at time 0. That's how you evaluate this antiderivative. And here we're going to get negative k times t minus 0. Then using our algebra rules from before, if we have two separate logs that are subtracted, that is the same as having the log of the two divided by each other. If we're looking at our algebra rules, I just used this one right here in reverse. I had two subtracted ones and I made them into the two divided. And that is going to be equal to negative kt. And so I did all of that funny math just so that when I show this, you'll see that actually once you know calculus, if you go further in physical sciences, which many of you will, you won't have to really memorize this integrated rate law. You will you will be able to get to it. Of course, for you guys, your tests and stuff are open book. You'll probably want to have this beside you, these integrated rate laws. They will be very useful. Now again, you don't need to know how to do that. I just like to show this for some of my students that have some calculus experience, that this can be determined directly from the rate law by integrating it. And that's what they mean by integrated rate law. So if you perform that integration on a first order equation, we can tell this is first order because it's the first power, you get this integrated rate law. If you ever wondered why there's natural logs all over this stuff, that's why. It comes from calculus. If it's a second order rate, well, your rate again is the change in concentration over the change in time. That's going to be k times the concentration squared because it's second order. And here the integrated rate law is 1 over the concentration of A at time t minus 1 over the initial concentration at time 0, and that equals positive kt there. K again being the rate constant, t being the time. And finally, for a zero order equation, the rate is always change in concentration A over change in T. That equals K times the concentration at time 0. And if you integrate that, you get concentration of A at times T minus concentration of A at times 0 equals negative KT. Again, you will always be provided these integrated rate laws. You don't have to do calculus like I just did. But these are the integrated rate laws, and the value of them is they give you a relationship between the concentrations at various times and how much time has passed. So, how will we use this? Well, it's exactly for this type of problem that we'd want to use this. So at 1000 degrees Celsius, cyclobutane decomposes in a first order reaction, so we know this is first order, with a very high rate constant, 87 seconds to the minus 1 power. And it makes 2 molecules of ethylene, C2H4. If the initial concentration is 2 molar, what is the concentration after 0.01 seconds? And what fraction has decomposed? So, we have to find the concentration of cyclobutane after a certain time, and that's what tips you off that you're going to be using the integrated rate law, the fact that time is involved. So we can, and I want to point something out to here. I'm doing this. I'm doing this on this slide to point something out because it can be confusing. And your book likes to mix these up for some reason and interchange them. This is the integrated rate law that I gave you, right? This means the same thing. Why does it mean the same thing? It's because if we take this and multiply it by -1, on both sides. That cancels this negative, and we get -1 times natural log. However, that's the same as saying natural log of concentration C4H8 at time t over concentration C4H8 at time 0 to the -1 power. And that is the same as natural log of C4H8 over C4H8 at time 0. Now we're flipping. When you put a fraction to the -1, that's the same as flipping it upside down. So at time t is on the bottom, and that will now equal positive kT, which is exactly this equation right here. So be careful not to get confused, and this is the reason why when I'm uncertain, like I haven't studied this in a while, and so I haven't memorized whether there's a negative here or not, I will often go through that whole process of integrating to double check for myself, and I think it's a good exercise if you know calculus. But for you guys, I'll always be giving you these equations, so you don't have to worry too much, but don't freak out if you see it like this. If the negative goes over here, that flips this fraction. Okay, so now we want to solve the question here. So for this question, we're going to be using the integrated rate law, and what we want to get, let's go back to the question and see what we want to get. Actually, I'd like to write this out before I show you guys here, and I have room. I left room on this slide to write it out. So what we want here in this is we're given the initial concentration, we're given the time, we want the concentration after a certain period of time. So we want the concentration at time t. So what we can do is we can solve this. What we're going to do is, you can do this multiple ways. On the next slide, I'm going to show you how you can do it if you just plug in numbers first. On this slide, I'm going to show you how you can actually just solve for what you want directly. I'm going to take e to the power of both sides. So e to the natural log here, and I want to make this a red one. E to the power of both sides. We're going to do that. And that's going to get rid of this natural log. So in terms of algebra rules, what I'm using here is this algebra rule right here. E the natural log cancels the natural log, and you get what's inside the natural log. So I'm using that, and so that gives me the concentration of C4H8 at time t over the concentration of C4H8 at time 0 equals e to the minus kt. And then I can multiply both sides by C4H8 initial at time 0. Then I get C4H8 at times t equals C4H8 at time 0 times e to the minus kt. And now I can plug in my values. So my initial concentration is 2.00 molar. And it's going to be e to the minus, my k is 0.0, my k is, I need an eraser here. That was my t. So my k was given right here, 87 seconds to the -1 power, which is 1 over seconds. I can write it that way too, either way. And then t was 0.0, I'm almost about to go past my head, 0.01 seconds. Okay, and so you can see now that the seconds are going to cancel, second divided by second, so there'll be no units in the top. Your units here will be molarities. And so now we can put this in our calculator. And for my calculator, I'm going to, for my calculator here, I'm going to do what's up in the E first. So I'm going to do 87, I'm going to make that negative, times 0.01, that equals negative 0.87. And I'm going to take e to the power of that. Whoops, not exp, e. Where's my e? So e to the power of 0.87, make that negative, and I get 0.418. Now I'm going to multiply that times 2, and I get 0.837. Okay. Or 0.838, I suppose. So my concentration, and that's molarities. So my concentration, and I'll use this spot since I still have it. My concentration of C4H8 at time t is 0.838 molar. And so there we have it there as well. Now, one note about Sig Figs, and it should, and now one thing is that I did a little bit different. I'll just kind of describe what I did here. So in this one, what I did was I put in the numbers first. Okay, and I calculated the numbers first, so I got 0.87 on the right. And then I took e to the power of 0.87. I got 2.4. Now let me explain to you the way the Sig Figs work here. And I'm going to give you guys a separate document that I'm going to put online that describes this. But there are different rules for Sig Figs for logs. When you take a log, your number of Sig Figs should be however many decimals past. So let's say I do log, 2.0. This has 2 Sig Figs, so my answer I should go 0.2 after the decimal. And I'll give you a whole separate document on this. I have a separate document that describes this. And if you're doing the opposite, and this could be ln too, log or ln, it doesn't matter. And if you're doing e to the power or 10 to the power and you're doing an exponent, however many decimals it has, like 0.87 here, your result should have that many Sig Figs. So that's why the 2.4 is appropriate there. And then at that point, you multiply both sides by C4H8 at time t, divide by 2.4, and you get about 0.83. And I think I would have gotten 0.84. Let me go back to the last slide. Yeah, so mine is 0.84. And this is all because there was a rounding in the middle, and I carried all my digits here. But they're the same answer, essentially. So you can do this either way. And I'm not too tough on you guys on Sig Fig rules for logs and for exponents, but I do note them because you might get confused about like, why are numbers different when you round so much? When you do exponents, the reason why you only do as many significant figures as there are places after the decimal point is because when you take an exponent, you usually blow a number up and make it way bigger. And so whichever rounding error you have gets blown up too. And so that's why you're not allowed to go too far past the decimal. You're only, so again, and I'll show you a separate document on this too, or I'll put it up in here in this section because it's pretty relevant to this. But when you're taking the log of a number, you write your result with as many decimal places after the decimal as you had Sig Figs. And when you take an exponent like e to the power 10 to the power of a decimal, here of a number, you write as many sig figs as it has places past the decimal. Since this had 2 past the decimal for sig figs, 2 sig figs, 2 past the decimal, we wrote a result with 2 sig figs, 2.4. And thus our final result had to have 2 sig figs. And so that's how you do that one. And then the second question asked, find the fraction that has decomposed. And so the 0.83 here, or 0.84, is what's left. And what you started with was 2 molars. So the amount that decomposed is the 2 molars minus the 0.83 molars. That's the amount of decomposed. Then you divide that by the amount that you started with. So the amount decomposed was the 2 molars minus 0.83 molars that you have left after that time period. Then you divide that by the value that you started with. And that's the fraction that decomposed. And so if we calculate that, 2 minus 0.83 equals divide by 2. We get 0.585, 0.59. Okay. So that is the reason why we use these integrated rate laws, because they can tell us what will be the concentration after a particular time, or how long will it take until the concentration decreases to a certain value or increases to a certain value. Now, in the last lecture, we had a way of determining the rate orders of reactions that was called the initial rates method. So we used the initial rates. There is another way to determine the order of the rate law, and you're going to do it this way in experiment 6. So in experiment 4, you use an initial rate style approach. But in experiment 6, which both of those we're going to be doing, or in experiment 6 we're going to be doing in person. In experiment 6, you use a graphical method like this. So the graphical method, the way it works is this. You look at the concentration over time for a particular reaction, and you plot that concentration versus time. You also plot the natural log of the concentration versus time. You also plot 1 over the concentration versus time. And the reason why you're going to do this is, I'll show you right now. If you look at this integrated rate law, if this is first order, we can rearrange this integrated rate law using algebra to be in a linear form. Let me show you what I mean. If we take this here, we can apply algebra rule, this algebra rule, where if you had 2 logs divided, it is equal to the separate logs subtracted. And we can make this look like this. Natural log of a at times t. Oops. I wanted the bracket on the other side there. So natural log of a at times t, time t, minus the natural log of a at times 0 equals negative kt. Then what we can do is we can add the natural log of a at times 0 to both sides. And so then what we get is this. On the left, so here these cancel, by the way. And all we have left on the left side is natural log of a at time t. And this equals negative kt plus natural log of a at time 0. And this is in a linear form. This is a straight line form. So I've just derived what you see here. And in this, notice that on the graph, the natural log of a times t is the y value. This is y. Okay. The slope is negative k. So this equals negative k. This is m. The t here is the x. That's the time. So this time is x. And now plus the natural log of a0, a times 0, the initial concentration, that is b. Y equals mx plus b. I'm going to make this y actually red. So your y-axis, if you plot the natural log of a at time t on the y-axis over here, and you plot time on the x-axis, then your slope will be the negative of the k, and your y-intercept will be your natural log of your initial concentration. And so if you plot the natural log of a at times t versus time and it is linear, that tells you that the reaction is first order. So besides the initial rate way before, where we did multiple experiments and compared them to figure out the rate order, we can also figure out the rate order by graphing the natural log of the concentration versus time. If it is linear, then we have a first order rate law. Likewise, we can figure out if it's second order rate law. Looking at the second order integrated rate law, we can, here, if we add to both sides, so plus 1 over a0 here, and add that to this side too, plus 1 over the initial concentration, then these here will cancel, and we will get on the left just, I don't know why this is beeping, we'll get just 1 over at here. Oh, wrong keys, that's why. So here, all we have left is just 1 over the concentration at time t. That is right there. On the right side, we have kt, and we have 1 over the initial concentration. That's right there. And this is also in a linear form. So if this guy, if you plot on the y-axis 1 divided by the concentration, that's the y. And then if you plot on the x-axis the time t, that's your x, then your slope is going to be k, the rate constant, and your y-intercept will be 1 over the initial concentration. That's b. I should have said m here, whoops. Y equals mx plus b. So the slope is k, the x value is time, so your x value is time, y value is 1 over the concentration. That means that the slope m is k, here, slope is k, and the y-intercept b right here is 1 over a0, 1 over the initial concentration. And so if you plot 1 divided by the concentration versus the time, and that comes out as a line, then you will know that your reaction is second order. So what you'll want to do to test is you'll do both. You'll have the concentration and time, you'll graph lateral log of concentration versus time, 1 over the concentration versus time. If it's so, and the plot of 1 over concentration versus time will give a straight line for a second order reaction. If you have a 0 order reaction, that one is kind of the simplest to show. If we add the initial concentration to both sides, so this was the original, all of these were the original rate laws that I gave you at the beginning. those will cancel. We need to add the initial concentration on this side. And so what we get here is all that's left on the left side here is the concentration at time t. This is all gone. On the right side is negative kT plus the initial concentration. So for zero order reactions, if you plot concentration on the y-axis, and on the x-axis you plot the time, then your slope will be negative k, and your y-intercept will be the initial concentration. And so if a plot of the concentration versus time gives you a straight line, then you have a zero order reaction. Whoops, this should say zero order. I need to fix that. Zero order reaction. And you can see here that, yes, in this graph, the concentration is on the y-axis, the time is on the x-axis. We have a slope of negative k, the negative of the rate constant, and the y-intercept is the initial concentration. So here's an example of data that shows this. So this is something you're going to be doing in your labs, and this is actually something we're going to be practicing this week using Excel on your experiment B, which is due at the end of the week. So you've got time and you've got concentration. So realistically, you'd be watching the concentration of the reactants versus the time. This is the natural log of the concentration. So if I took the natural log of, oops, right here, if I took the natural log of 0.0165, 0.0165, and I take the natural log of it, I get negative 4.104. And this is 1 divided by the concentration. So 1 divided by 0.0165. I get 60.6. And you do this along your whole reaction, and then you plot it. So here's the plot of the concentration versus the time. It's not linear, it's curved, so this reaction is not zero order. Here's the concentration of natural log of the concentration versus time. So here's natural log on the y-axis, natural log of concentration. This is the y-axis. The x-axis is again the time, and you see you get a line. It's negative in slope because the slope is negative of the rate constant. And so this reaction must be first order because your natural log of concentration versus time gave you a straight line. To see if it's second order, you plot 1 over the concentration versus time, and this is clearly not linear. And we're going to use Excel to do this. This would obviously be very labor intensive to do this by hand, but we'll use Excel to calculate the natural log, calculate 1 over the concentration, and so forth. And so that's how you can use the integrated rate law and graphing these values here. You record these and then you calculate these and graph them. And we can use that to determine if the reaction is zero, first, or second order. Finally, half-life. So we first encountered the term half-life in the nuclear chapter, and it applies the same way here. It's the time it takes until you have half of your initial value of reactant. So that could be a nuclear reactant that's undergoing a nuclear decay process. It could also be a chemical reactant that's undergoing a chemical reaction. So one interesting thing is that for a first order reaction, the half-life doesn't depend on the starting concentration. And that is why the half-life of radioactive materials doesn't depend on that amount that you start with. is because it's a first order process. So as I demonstrated to you before, the half-life for a first order reaction is the natural log of 2 over k. Natural log of 2 is 0.693. This is for a first order reaction. And for a first order reaction, the half-life is constant, but for second order, it's not. But that's why the half-life is very, very useful in terms of radioactive decay, and that's why we first encountered it there. But it's also a concept that comes into play for kinetics of chemical reactions as well. And so we can see here the progress of a chemical reaction in terms of half-life. For a first order reaction, again, the half-life is not going to change over the course of the reaction. So what this is indicating is that for this first order reaction, over its half-life is 24 seconds. So over the first 24 seconds, half the initial concentration is used up, and the concentration drops from 0.6 molar down to 0.06 molar down to 0.03. Then over the second half-life, another 24 seconds, the concentration gets cut in half again. It goes down from 0.03 down to half of that, 0.015. Then in the next 24, not seconds, but minutes rather. I didn't see there, it was minutes, but either way, another 24 minutes, another half-life is passed. Again, the concentration is cut in half, down from 0.15 down to 0.015 down to 0.0075. Basically every time a half-life passes, the concentration gets cut in half. So how can we use this information? Here's an example. This is gonna very much be like what we did in the nuclear chapter. So we've got a first order process here. And it's a cyclopropane. It's very strained in this triangle formation, so it wants to break open. So it's thermally unstable, and it will rearrange and form something else, and it's a first order reaction. The rate constant here is given as 9.2 inverse seconds. What is the half-life of the reaction? Well, since this is first order, we can use that equation. The half-life is the natural log of 2 over the rate constant, which we will use here. Once we know the half-life, we can figure out what it will take to reach 1/4 of the initial value. Of course, we could find that directly, but since we have the half-life, 1/4 is what you get after 2 half-lives. So that would be a kind of simplified way of doing it for this problem. We did kind of more complicated example in the nuclear chapter. So let's figure out the half-life. We got the rate constant here, 9.2 inverse seconds. So the half-life will be the natural log of 2, or 0.693, divided by the rate constant. So we put the rate constant in, 9.2 inverse seconds. So remember, inverse seconds is 1 over seconds. So in terms of units, we have 1 over seconds, or this is the same as 1 over second, 1 times seconds over 1, or just seconds. So our units will be seconds, and for our value, it will be 0.693, or the natural log of 2. We should just do that, actually. Your book really likes to skip that natural log of 2 too, I noticed, but natural log of 2 is 0.693 divided by 9.2. And we get 0.075, and the unit here is seconds. So in order for the substance to go to 1/4 of its initial value, that means 2 half-lives must have passed. So this is 1 half-life. It will be 2 half-lives, so we multiply this times 2, and we get 0.150 seconds. 0.15 seconds to 2 Sig Figs. And so one thing I want to say a little bit more about half-life equations, because you were introduced to the first order half-life in the nuclear chapter, but now we're going to have second order half-lives. So here we have the second order half-life is 1 over the rate constant times the initial concentration. So notice that the first order half-life did not depend on the initial concentration. Again, that's why it makes it useful for describing nuclear processes, that the half-life doesn't depend on the initial concentration. But for a second order reaction, it does. Why is that? Well, let me derive it for you in the same way that I did for the first order half-life in the nuclear chapter. So if we're using the integrated rate law for second order, the second order integrated rate law, and you don't have to memorize this, you will always be given it, but it looks like this. So this is what I gave you on the very first slide. And remember what half-life means. So at the half-life, this means half-life means T1 half means the concentration of A at time T is 1/2 of the initial concentration. So we're going to substitute that in for the concentration at time T. It's going to go right here. And so what we get there is 1 over 1/2 times the initial concentration minus 1 over the initial concentration equals kT. And here what we have is 1 over 1/2. So 1 over 1/2, remember when you divide by a fraction, that's the same as multiplying by the reciprocal, so 1 times 2 over 1, that is 2. So what we've got is 2 over the initial concentration minus 1 over the initial concentration. And if you remember subtracting fractions, if they have the same common denominator, then we can subtract them like this, 2 minus 1 over the initial concentration because they have the same denominator, equals kT. So this is 1 over the initial concentration equals kT. And this T now is not just any T, it's the half-life. It's the T1 half. Because we're talking about the time when the concentration is half the initial concentration. That is what the half-life is. So now if we divide both sides by K, we'll get 1 over K times the initial concentration equals T1 half. I'll tell you guys, this equation right here, I will memorize it every time I'm teaching it and then promptly forget it because I hardly ever use it, and also because I know what half-life means, so I can get it anytime I want as long as I have the integrated rate law. So this is the equation that relates the rate constant for a second order reaction to the half-life. It depends on the initial concentration. For a zero order reaction, I encourage you to figure it out for the zero order reaction yourself. So do just like I did and ask me if you have questions. For the zero order reaction, the integrated rate law is the concentration of A at time T times the concentration of A times 0, or minus the concentration of A at time 0 equals negative kT. You should be able to use that to determine the half-life. Make sure to plug in for A at time T. You'll have 1/2 of the initial concentration, just like I did here. So you'd plug that in here, and your T would be T1 half. And you should be able to figure this out. So in summary, the integrated rate law equations I gave you at the beginning, I'll give them to you. From those, we were able to determine several things. We were able to determine the units that we would have for K depending on which order of reaction we have. We were able to get formulas that relate the rate constant K to the half-life. we were able to put the integrated rate laws into a form where they could be graphed linearly. And so we could check if a reaction is zero order, first order, or second order based on whether a graph is linear. If a graph of the concentration versus time is linear, that means you have a zero order reaction. If a graph of the natural log of concentration versus time is linear, that means you have a first order reaction. If a graph of 1 over concentration versus time is linear, that means you have a second order reaction. And the slopes would be here respectively. And so I showed how you could derive that from the initial equations that you'd be provided. And this is shown, these are the same graphs that we looked at. And so that's a summary of what we learned here with integrated rate law. And now you should be ready to tackle some problems like we did here. And of course, we'll have normal office hours, so please come and see me at office hours or ask me questions if you have any. Yeah, and I'll see you soon. We'll have one more video coming out early this week about experiment B. And all right, have a good one, guys.